Okay, so here's some work about with around probabilities that I thought I'd do instead of using our textbook. So you want to make sure that you will get these ideas down. Make sure you make yourself a set of notes for this vocab. You want to be familiar with this notation about not and then what P of A means, and then the professor who wrote this is from Champlain College, and he uses some terminology that's a little different. This classical approach, you could think of classical as being theoretical, so that's based on theory. And as you probably did way back, with Mrs. Wozni, the number of ways that success can occur divided by the total number of events. So if I want to know what's the probability of rolling a 1 on a die, on a 6-sided die, it would be 1 out of 6. If I wanted to talk about the probability of rolling an even number on a die, that would be, there's 3 even numbers, 2, 4, and 6. So that would be 3 out of 6, or 1/2. Okay, so I would write that as probability of an even would be equal to 1/2, or 3 out of 6. Okay, so you get that idea. I mean, it's not anything new, it's not stuff you've seen before. So sample space might be a new word. Sample space is the number of ways that something can occur, and it's all based on theory, not based on observed things. And then, of course, the complement is 1 minus the probability of something happening. So I mean that's nothing new. So this trick here about coming up with the probabilities of how, if you're flipping a coin 3 times or 3 coins all at once, what's the probability of getting counting the number of heads that you observe when you flip 3 coins. One way to do this from this classical approach or theoretical approach is to make a tree diagram where this is if the first coin flips a head or a tail, you put those down. Then on the second flip, you draw a branch for head or tail. Then the third one's another branch off each of those. Then you're just listing the outcomes. And then, of course, he didn't fill in this table for us in the notes, so I'm going to do it now. What's the probability of getting 0 heads? Well, that only happens once down here. So 1 out of how many different outcomes? I believe it's 8. 2, 4, 6, 8. So 1 out of 8. What's the probability of getting seeing one head? Well, let's see. So that's a situation. Whoops, that's too big. Be able to go to this. There's a situation, an outcome, a result where there's only 1 head showing up, and same thing there, and same thing there. So that's going to be 3 out of 8. And then for 2 heads, that happened there, that happened there, that happened there. So that's the same, 3 out of 8. And then all 3 heads, that only happened once, so 1 out of 8. Then what I want you to ask yourself is, what do all these probabilities add up to? Well, hopefully you realize you're 1, right? Okay, so here's question number 2 for our turn. So I don't think we need to do a tree diagram for this problem. Let's see. You go enter a lottery by purchasing 1 out of 200 tickets. They're going to do 1 grand prize, then 5 other small prizes. So what's the probability I'm going to win the grand prize? Well, I hope you're thinking it's 1 out of 200. And what's the probability that wins a prize of some type? Well, there's a 1 way to win the grand prize. There are 5 other tickets that are winners. So isn't that 6 out of 200? And what's the probability they don't win anything at all? Well, that's that whole idea of the complement. What's 1 minus 6 out of 200? Well, that's 9. That's 100. 200. Here, let me erase that. 200 out of 200 is 1. Minus the 6 out of 200. So that's 194 out of 200 is the probability that we won't win anything. And that's all theoretical. And this is why people buy the lottery tickets. That's why I buy a lottery ticket once in a while, is in the long run you don't win, but once in a while in the short run, who knows? So now he's having us move on to relative frequency of probabilities, and that's when you're using collected data to estimate a probability. What I did here is I pointed out here's the relative frequency way to come up with a probability, and notice how it's worded. Notice how it says the number of ways, the number of times a trial was completed, versus theoretical says the number of different ways in the sample space. Now that's why I guess I didn't say that, but that's what it's implying. So this is sample space. This is how many you can see. So if I'm rolling a die 100 times, that would be 100. Whereas usually with a die, it'd be out of 6. Okay, so see how that's this when you're dealing with relative frequency probabilities, this bottom number could be anything. And you just divide it to make the percentage or the proportion, or you could leave it as a fraction simplified. Okay, so that's the difference between theoretical or classical versus relative frequency probabilities. So Shaquille O'Neal made this many out of that many free throws. So what's his relative frequency estimate of his probability of making a free throw? So 570 out of 10,895. Grab a calculator, make it a decimal. It'll make more sense. And let's see. So our turn. Out of 200 people that walked by your store on Church Street, where's Church Street, folks? Over the past hour, 15 of them entered the store. So estimate the probability that the next person coming down the street will walk into the store. Well, how many of the last 200 people did? 15 out of 200, and that's our relative frequency probability. Now, here's probably the most important thing that you're going to learn in this course, this law of large numbers. The law of large numbers says as you repeat a trial or an experiment over and over and over again, the relative frequency probability will approach the actual probability. Which is different from that law of averages, and we'll talk about that in class, and maybe I'll have you do some reading about that too. So the law of large numbers says the more often we repeat trials or do more and more trials, our estimate will approach theoretical probabilities. And then this rounding off rule is just something he was using for his book. Oh, and subjective probabilities are basically based on your feelings. So what's the probability that you're going to pass this course? Well, for some of you might feel it's kind of low. For some of you might feel it's kind of high, and the reality is probably somewhere in between. Okay, so that's subjective. What's the probability we're going to have a snow day on this Wednesday? I'm recording this on a Monday. Actually, it's Monday the 16th in 2017. We're supposed to be getting a storm on Tuesday night and a Wednesday, so we'll see. So that's subjective. So now conditional probabilities can be hard. I mean, you certainly look at that notation. That looks awfully confusing, but it isn't that bad, especially if we think about it from a relative frequency situation. We aren't here. We're going to do this is actually theoretical, the classical, because we know the outcomes. We pick one card from a deck. What's a probability that is a jack, given that it is a heart? Well, some of you are going to say, well, let's see, there's 4 jacks out of 52 cards. That would be wouldn't be a conditional probability. What they are telling us is what's the probability the card will be a jack given that it's a heart. Well, there's 13 hearts, and there is only 1 jack out of the 13. Now, it just so happens that this probability and that probability are the same. However, that's a fluke. That will not always happen. If we look at question number 2 here, here's the situation. If you pick a card from a deck, what's the probability that it is a heart given that it's a jack? Well, there's only 4 jacks and there's 4 suits, so only one of those, one card in each suit is going to be a jack, so 1 out of 4. So that's not quite what we were thinking of. Now this whole idea of without replacement or with replacement, without replacement means you're going to draw a card out of the deck and not put it back in. So to answer this question, first off, there's 52 cards, and then we're going to draw a card out. And now let's assume it says the first card was a jack. So there's 4 ways we could draw a jack out of the deck out of 52. So now to answer this question, how many cards are left in the deck? Well, there's 51 cards left in the deck. How many of those cards are jacks? Well, we already took a jack out, so that means there's only 3 left. So you see how this result depends, is based on a condition of what we take out the first time. So that's why one way to think about it is conditional probability. So for this next question, it's a your turn question. Why don't we read it, and you can think about it, and then I'll stop the video and you try it, and then I'll do it for you. We're picking 2 cards out of a deck without replacements. That means what? And what's the probability the second card is jack, given that the first card you picked was a queen? If you think of what we did up here, you should be able to answer this question. Why don't you stop the video, try to answer it, then come back and watch my answer. So I'm assuming you stopped the video and actually did this. So there's 52 cards in the deck to begin with. I want to know, the answer I'm trying to do is, what's the probability that there's a jack on the second card? Well, I'm picking a queen. So how many jacks am I taking out? Absolutely none. So on the second draw, there's only 51 cards left, and how many jacks are left in the deck? Well, there's still 4 jacks left in the deck because the first card was a queen. So it's not the same probability as the problem I just did, because there's a different condition that's going on. Now, if I pick 2 cards from a deck with replacement, that means I'm putting it back in as they tell you. What's the probability that the second card is a jack, given the first card is the jack? Well, if I'm drawing with replacement, that means that for what I did the first time really doesn't matter, as long as I'm shuffling them up well. So on the second trial, there's still 52 cards in the deck, and there's still 4 jacks. So that, which is equal to 1 out of 13, which is some decimal, is the probability of that question. So now we're going to look at conditional probability with a little bit different twist. This is based on a table of data, so this is a frequency probability, a relative frequency probability, because we're using it based on data. So we're trying, what's the probability that some test device says somebody has cancer when they really don't, so it's a false positive. So what we're doing is, what's the probability that somebody has a positive test result given that they do not have cancer? So how many people don't have cancer? Well, there's 200 people that didn't have cancer. And how many of those 200 people got a positive test result? I'm seeing 20. So the probability that we got a false positive is 20 out of 200, or 1/10, or 10%. Not very good. I'd be kind of worried about that. What's the probability that somebody has a false negative? I wonder if that's a more scary thing. I don't know. So a false negative would be what somebody tests negative given that they have cancer. So there are 200 people that had cancer, and 2 of those people, the test said did not. So again, 2 out of 100 is 1 out of 100, so 1%. A 1% chance of getting a false negative. Oh, this is an interesting answer question. What's it suggest about the screening device? Was certainly erring on the side of caution as far as getting people treatment. So for this one, sorry, I didn't realize the tape, the recording was still going. The way this is worded is always a little strange. So there's 400 people total. If you go back up to this one, how many people got a false positive? Well, there were 20 people that got a false positive. They didn't have cancer, but the test said yes. So they haven't had the screening yet. So what's the probability here? Well, it'll just be 20 out of 400. But now we're getting, so that's not a conditional probability. That's just a straight probability. Now that we're going to do, hey, they got a positive test result. What's the probability of a false positive? That's where we're going to do the 20 out of 200. Okay. This next one says, suppose you go to a screening and the test comes back positive. The doctor tells you there's a 5% chance that the result is wrong or is not correct. Is the doctor wrong? Well, let's see. You go for screening, the results comes back positive. So the doctor's doing is he's using this 5% figure when he really should be talking about this figure where there's the person came back with a positive test result. So they already went in and had the test. So they came back with a positive test result. And there's almost a 10% or 10% chance that they got it wrong. That the test is saying they've got cancer when they really don't. So that's what's happening there. Okay, so the addition rule is the probability of event A and or event B happening is the probability event A plus the probability event B minus the probability of them both happening at the same time, A and B. Okay. So what's the probability that a card's drawn from a standard deck? Theoretical probability, right? Find the probability as a king or a queen. So, well, what's the probability of it being a king? 4 kings in a deck of 52. What's the probability of being a queen? 4 out of 52. What's the probability of being both a king and a queen? 0 out of 52. And so that would give me a probability of 8 out of 52, which we could reduce. We grab a calculator. 4 out of 13. No, 2 out of 13 is, I think, what that reduces to. Okay. The event, the card being both a king and a queen is something that's called mutually exclusive. See, they start talking about it down here. And when things can't happen at the same time. You can't be pregnant and not pregnant at the same time. You're one or the other. You can't be a junior. Well, that's probably a bad example. You can't be a high school graduate and not be a high school graduate at the same time. let's see. So what's probably a king or a heart? So let's see. So how many kings are there in a deck? Well, there's 4 out of 52. How many hearts are there in a deck? Well, there's 13 cards in each suite, in each suit. No, 14 times 3 is 52, right? Now, there is a king of hearts. So there's a there isn't a probability that it's both a king and a heart. So I'm going to subtract 1 out of 52 from the math, from the straight formula way. You might think about this in a little bit different manner. So let's see, 4 plus 13 is 17, minus the 1 that's in common is going to be 16 out of 52, which we could reduce. I'm not going to. Okay, so we talked about mutually exclusive already. All right, good enough here. So here he wrote the formula for the mutually exclusive in the mutually exclusive addition rule and the regular one. Okay. So you don't want to make sure we don't count everything twice. That's this thing. Taking away, subtracting off the ones that fall into both criteria. Okay. Guess that's it for this page. Okay, I'm pretty sure this is strange. I wonder if I did something weird with the copying, because this we just did, but we didn't do this. So let's just jump down here to number 3. All right. So, and I left the answer on there. Okay, that's okay. So we got 2,400 students. Small private New England college. This guy teaches at Champlain, so I wonder what college he's talking about. Oh, let's see. If a student selected at random, what's the probability of selecting a male or freshman? So you get a male freshman. So how many males are there? Oh, 1040. Out of the total, if we want, we can do some shortcuts. What's the probability that a student is a freshman? So there's that. So 575 minus, don't want to count this number twice, so I'm going to subtract off the 255, and this is all out of the total of 2,400, and that's how you calculate that probability. So these next couple are your returns. Once you stop the video, try to check out what numbers you're going to use, and then see if you can't calculate this probability. And then, of course, come on back and watch what I do. So, we're out of 2,400 students. How many females are there? Well, let's see. I'm seeing 1,360. And how many seniors are there? I'm counting 425. But I got to subtract off the 260 female seniors. And that's how you get that probability. How about a junior or a senior? Well, let's see. How many juniors are there? Counting 475. How many seniors are there? Well, we saw that there's 425. Is it possible to be both a junior and a senior? No, it is not. Those are mutually exclusive events. So that's how you calculate that probability. So I'm not going to read this page to you, but some things you want to pay attention to is about how when you're going to use the multiplication rule, when there's an and, with the addition rule, it was this or that. Now it's the and part, this and that. We multiply. And then you want to make sure you understand independent and sampling without replacement, and how dependent events are sampling. I did that backwards. Independent are sampling with replacement, so you're putting it back in so the probabilities don't change. And dependent events are synonymous with sampling without replacement, because as soon as you pull one marble out, the probabilities drawn the next one change. Okay, so let's keep going. Then they give us this conditional probability formula again, and because the multiplication rule is the same as the probability of event A happening times the probability that event B happens, given that event A happens. It sounds confusing. It's not bad once you start looking at tables and doing that. Okay. All right. So this situation, we've got what? We've got 4 red marbles and 4 green marbles. That means the box contains 8 marbles all told. So we're going to calculate some probabilities here. I meant to white this out, but that's okay. See how we're sampling with replacement, so that means we're putting the marbles back in. That makes it an independent. The two probabilities are independent. So what's the probability they get a red marble on the first draw? Well, the first draw there are, let's see, we're looking for a red marble, so there's 4 marbles in the bin. 4 red marbles in the bin out of 8. And then what's the probability of getting the next one? Well, let's see. Again, we've put the marbles back in, so there's 4 out of 8 again, because there's still 4 red marbles in there. If we do some reducing to keep these numbers easier, I'm just going to write this is 1/2 times 1/2, which is 1/4. Okay, now if we're going to sample without replacement, these are dependent events, as it says. So for the first draw, there's still 4 red marbles and 8 marbles total. But now, because we're not putting marbles back in, we're going to assume we got a red marble in the first draw. So that means there's only 3 left, and that means there's only 7 marbles left in the bin. Now nothing cancels there. Well, we could say, right, this is 1/2, I guess. 1/2 times 3/7. So that makes the probability 3 out of 14. So quite a bit difference in the 1/4. Well, I guess not. 3 out of 14 is close to 1/4, so it's not that big a change. Let's see. If you sample with 2 marbles without replacement, so that means these are dependent events. Let's probably get a red marble in the first draw and a green marble in the second. So I'm going to let you stop the video, think about this. And then come back and get the answer, and then come back and see my answer and see if we agree. So I'm going to say that there are 4 red marbles on the first draw, and then there are 4 green marbles, because we haven't pulled the green marble out, but there's only 7 marbles left in the bin. So a couple of things we can simplify here. I'm going to do some arithmetic. That's going to be 1, that'll be 2. 2 goes into 4 twice. 2 times 1 is 2. 1 times 7 is 7. So 2 out of 7 is that probability. Okay, let's see what else he's got for us to do here. The extended multiplication, I don't remember you even worded it this way, just means you can multiply each of these probabilities. Okay, and so a box contains 4 red, 4 green. Let's see, if I have 3 marbles with if I select 3 marbles with the replacement, so that means I'm putting them back in. So there's 4 red marbles to begin with out of 8. I'm going to put it back in. So there's 4 ways to win out of 8 again. And then there's 4 ways to win out of 8 again. I've done 3 draws. I wrote down the probabilities, so I'm just going to multiply them. Now some things I can do to make my work easier. This is 1/2 times 1/2 times 1/2, which is the same as 1/2 to the third, if you want to think about it that way. So that's 1/8. And let's see, we had an alarm clock that works 90% of the days it sets. What's the probability that it'll work 5 days in a row? Well, what's the probability that it'll work the first day? 0.9. And then for the second day, 0.9. That probability doesn't change. So these are independent events. And because I don't want to write out 0.95 times, I'm just going to raise that to the 5th power because it's 5 days. And on my calculator, what does that tell me the answer is? 0.9 raised to the fifth. I got 0.59049. So let's see. We got some more things to do. Let's see. So we got 3 marbles without replacement. There are 8 marbles total again. What's probably all red marbles. So for the first draw, there's 4 out of 8. I pulled a marble out, and I pulled a red marble out, we're assuming. And I pulled another red marble out. So for the first draw, there's 4 ways out of 8 marbles. There's only 3 ways to win. There's only 7 marbles left. And there's only 2 marbles left for the third draw out of 6 marbles. Two red marbles out of 6 total in the box. And then I guess we could do some arithmetic. Let's see. That's 1/2. That's 2. That's 2. And that 2's cancel. So I'm left with 1 out of 7, I believe, because it's 1 times 1 times 1 over 1 times 7 times 1. So here's your turn. Go ahead and read it, try it, see what you get. Come back and check my answers. So we're drawing 4 marbles without replacement. What's the probability of getting all red marbles? Well, first draw, 4 out of 8. Second draw, 3 out of 7. Third draw, 2 out of 6. Last draw, 1 out of 5. And we could do a bunch of simplification here. Well, maybe not as much as I'm thinking. Let's see. That's 3, and that's 1. That 3 goes away. And that's 1/2. Anything else I can cancel out? I'm not seeing it. So 1 times 1 times 1 times 1 is 1. And 2 times 7 is 14, times 5 is 70. Not very likely. This is almost the same kind of math as the probabilities of drawing your Megabucks tickets or Powerball tickets. So we'll look at that too later on. So unlike a bag of marbles, the population in the U.S. workforce is millions of people large. So if I'm take a few of them out and don't replace them, it's really you haven't changed the probabilities hardly at all. So that's why they're talking about this as being independent. So if my sample size is no more than 5% of the population, we can treat these as independent. And so basically these are it's like sampling with replacement. So if 85% of the U.S. workforce drives to work, what's the probability of randomly selecting 3 different people who drive to work? Well, the probability that somebody drives to work is 0.85. 85% is a decimal. And we're going to draw 3 of them. So I could write out 0.85 3 times or just raise that to the 3rd power. So 0.85 raised to the 3rd is I'm getting 0.614125. And then using the multiplication calculator, let's look at this. I haven't done that today. Drawing Jack of Hearts is 1 card is randomly selected from the deck. Well, I'm not seeing how this is the multiplication rule because you're only talking about 1 draw. I don't know, maybe I'm not looking at this right, but I see there's 1 Jack of Hearts out of 52 cards. I don't see why I'm using the multiplication rule with that. That's what I'm going to go with. Okay, the finding probabilities of at least 1 is, it seems complicated, but once you catch the idea, it's really easy. If I want so if I know the probability, 10% of apples are bad. I'm going to buy a bag. What's the probability of buying a bag of 10 apples? What's the probability that at least 1 apple is bad? Well, I would have to know the probability of 1 apple being bad, plus the probability of 2 apples being bad, plus the probability of 3 apples being bad, and add those all up. But couldn't I do this and treat this like a complement? If I could find the probability that no apples are bad, and then take that away from 1, won't this include all these other probabilities all the way up through probability of 10 apples bad? And that's what we're going to do, and that's what he's saying here. So he's saying the probability of not A. So that's the probability of the complement happening. So if we come back and take a look at these problems, let me do some erasing. So if 10% of the apples are bad, that means 90% of them are not. And if we've got 10 apples in that bag, what's the probability that all 10 of them will not be bad? Well, just take 0.9 and raise it to the 10th power. So 0.9 raised to the 10th. Why am I raising it to the 10th power? Because there's 10 apples, right? So that worked out to be 0.34867 yada yada yada. And now we're going to subtract that from 1, and that'll account for the probabilities of all the other events. So 1 minus that answer is going to be 0.651ish. Okay, here's another one. Suppose 3 cheap smoke detectors. Each one has a 90% chance of working. So let's find the probability of it not working. Well, let's see. If there's a probability of 90% chance of working, the probability of not working is 1 minus that, so 0.1. And we're going to buy 3 of these beasts. So 0.1 to the 3rd power will be the probability that all 3 of them will not work. So I'm getting 0.00. I should have been able to do that one in my head. And then I'm going to subtract that from 1. So isn't that 0.999? So almost a 99.9% chance of your fire detector working, even if you buy cheap ones in your home. And that's why redundancy is good. I mean, that's a pretty high probability. So here's your turn problem. 20% of the students know how to perform a correlation test. You don't yet. You will. So you're going to select a random selection of 5 students, and you're going to calculate this probability at least 1. And I'll let you think about these. You know everything you need to do in order to do this. This question, I'll admit, I'm not really thrilled about, but give it a whirl, come back and see how I did them. Okay, so what's the probability that at least 1 student knows how to run this test? Well, the probability that a student doesn't know how to run the test is 0.8. So there's 5 students, so this would represent the probability that none of the students know how to run the test. So if we subtract that from 1, that'll be that probability they're looking for, which is, just out of curiosity, 1 minus 0.8 to the 5th power, 0.672, whoops, I gotta need a pen, 0.67232. And then they told us this probability, and we are going to do this next, learn about this next. And then what's the probability that all 5 students know how to run the test? Well, each student has a probability of 0.2, so 0.2 to the 5th, that's almost 0. I mean, the calculator's in it. I'm going to do what my calculator's telling me, and then I'm going to talk about how to be smarter than the calculator. That's what the calculator's telling me. Remember, this means 0.32 times 10 times 10 raised to the negative 4, which means move that decimal point over to the left 4 times, so that becomes 0.00032. So a pretty small probability. Not 0, but it's getting close. So as far as completing the task, well, as long as at least one of your group members know how to do the task, you can get the project done. So that, I would say, that's why I think that's the pertinent probability. So that's all the notes in this section. I'm going to expect you to have the problems done at the end. Hopefully doing it this way will help.